Hey guys, welcome to Crown's Maths. In this video, we want to be talking about topology. But before we talk about topology, we have to first understand power sets and class. Now, power sets, let's say, given a set X. Let's say given a set X. Now, the power set of X is denoted as P of X or 2 raised to the power of X. So this is the notations for power set. Now, power set is simply the collection of all the possible subsets of what? The set X. Okay, a power set of a set is simply the collection of all the possible subsets of the what? Of the set X. So let's say if our set X is the sets AB, okay, so the power set of the set AB is simply the collection or the set of all subsets of this set X. So we have the singleton A, the singleton B, we have the set, we have the whole set, we also have the empty set, and of course this is the power set. Another way of knowing the number of elements in this set of the power set is simply doing 2 raised to the number of element in the set X. What's the number of elements in the set X? AB. AB are elements, so they are 1, 2. So definitely I'm going to do 2 raised to the power of 2. This will give me 4. So 1, 2, 3, 4. This is complete. So let's say if we have the set X to be the set A, B, C. Okay, this has what? 3 elements, 1, 2, 3. So we're going to have 2 raised to the power of 3, which is going to give me 8. So the power set is going to contain this going to be the set of 8 possible what? Subsets of what? This set X. That is, all the possible subsets you can form from this is going to be 8 in number. So let's form this. So we're going to have the empty set. We're going to have the set itself. The set itself is a subset of X. So we're going to have singleton A, we're going to have singleton B, we're going to have singleton C. Okay, we're going to have AB, the set AB, we're going to have the set AC, and also we're going to have the set BC. Okay, let's check if this is 8. 1, 2, 3, 4, 5, 6, 7, 8. And of course, that is it. So that's the power set. The power set is simply the set of all the possible subsets of what? Of this set X. Now, a class, on the other hand, a power set may be a class, okay, but a class does not necessarily mean a power set. A class means set containing what? A set. So a class, let me call this C1. C1 could be a class. So it's a set containing maybe only the empty set and the whole set. This is a class. It is a set containing what? Set. So I can have another one again, C2. C2 may be a set containing only the singleton set. It's also a class. Okay, so a class is simply a set containing what? A set. So we move over to topology. Now, reason why I introduced this is because topology is actually a class. Okay, so it's actually a class. Okay, now we say tau is said to be a topology on X if it satisfies the following axioms. Okay, so we say tau. First of all, let me give a formal definition. Okay, definition. Let X not equal to what? Empty. Now we let S not to be empty, and we say tau is a topology on X if it satisfies the following. It satisfies the following what? Axioms or properties. Now, the first property is that the empty set must be in tau. That's the first property. The second property is that the whole set must also be in tau. Okay. Now remember that tau is a class. Okay. Now the third property is that if this finite sequence, if this finite sequence is a subset of tau, then the finite intersection of this sequence is in tau. Okay, so if this finite sequence is a subset of tau, then their finite intersection is in tau. Okay, and lastly, if the arbitrary sets or sequence, could be a set, it could be a sequence, if this arbitrary sequence is a subset of tau, then the arbitrary union is in what? Is in tau. Then the arbitrary union is in what? Tau. Now, once it satisfies these four conditions, then we can now say it's a topology on what? On the set X. Now, the pair X tau is called the topological space. Is called a topological space. Please don't mind my handwriting. So this is actually called a topological space. Now, also observe that tau here is a class. Like I said, it's a class. Now, once these four conditions are satisfied, we call it what? A topological space. A topology on X. Now, an example of a topological space, we have a discrete topology. We have a discrete topology. We have the indiscrete topology. So let me give you these examples of topology. So watch this. So we have we have the indiscrete topology. The indiscrete topology is a topology containing the whole set and the empty sets. So the first one is the indiscrete topology. Indiscrete topology. So indiscrete topology. Now, the indiscrete topology is the topology containing the what? The whole set and the what? And the empty set. So this is also called the trivial topology. Why is this called the indiscrete? Because the only open sets in the topology are the whole set and the empty set. And this is a topology on any arbitrary set X. Okay? Now, observe that the sets inside the topology are open sets. Okay, all these are what? Open sets. Now, the second one is the discrete topology. The discrete topology. Now, the discrete topology is actually the power set of a set. Let's say X, let X be what? A non-empty set. So the power set of that set is also a topology. So you see that the power set is also what? A topology, because it satisfies the four properties. Now look at the first one. For the first condition, the empty set and the whole set must be in the set. It is already here. Arbitrary union. If I do this union, this, what do I have? X is inside here, right? If I do finite intersection, do the intersection of these two is empty. It's already inside the topology. So this is already a topology. So this one is also what? A topology. An example. Let's say let X be the set AB, and the power set of X is simply empty whole set singleton A, singleton B. Okay, now let's see, this is just an example. Let's say if this satisfies the condition of being of this being a topology, the empty set and the whole set is already in there. Now if I do a finite intersection, take any finite intersection here. Take any finite intersection. Let us say this intersect this. What do I? Okay, sorry, this is not complete. Okay, yes, it's complete. This intersect this. The intersection of this and this will give me what? Empty. So you see that the empty is already what? Is already inside the topology. So if we do any finite intersection, we are going to see that the result will still be inside this power set, which also makes it what? A topology. Now do arbitrary union. Take any union of your choice. Okay, if you want, add everything, do the union of everything, you will still get a result inside this set. So this power set is also what? A topology. Okay, and we also have another one again, another topology, which is the cofinite topology. Now the cofinite topology, let me call it tau p, just a notation, is defined as the collection of a subset of x such that a is equal to a is empty or a complement is what? Is finite. So this is a cofinite what? Topology. It is the collection of a subset of x such that a is either the empty set or its complement is what? Finite. So this is another example of topology. Okay, now one thing you need to understand that the topology is simply the set of open sets. Okay, topology is simply the set of what? An open what? Set. Now let's just do a random example to form a topology. Let's just form a random topology. Let's say given an arbitrary set S, can we form a topology on that set X? Remember, you can form as many as possible, as many topology you want on a set, given on a single set X. Let's say if I have a set X to be, let's say 1, 2, 3, 4. Okay, this is set X to be this. I can form as many topology I want on this. Okay, now of course, if I form, let me call this tau 1. Now I can form a trivial topology on this, which is the empty and the whole sets. Okay, this is a topology on this set. Okay, now I can form another topology on this, which is going to be the power set of this X. Okay, the power set of this X is also another topology on this set X. Now let's form something different from these two. Okay, now of course, by definition of topology, the empty set must be there, the whole set must be there. Now if I take let's put singleton 1 and let's do singleton let's not do singlet 3 and 4. Okay, now watch. If I do the intersection of these two, what do I get? I get the empty set, right? If I do their union, okay, their union is not actually here. If I do their union, I'll have 1, 3 and 4. Okay, I have 1, 3 and 4. So this is actually a topology. Okay, so if I do the intersection, I have the empty. If I do their union, I have this. So definitely this has formed what? A topology. This is also a topology. So you can form as many as possible a topology on what? On this X. Thank you very much.